Hello, it's Goffloy again with another project for RF Project 14 in November 2019. This time it's antenna modification on the IDT SDAWIR wireless flow rate, humidity and temperature sensing evaluation kit, featuring the Molex antenna sample kit. I did a road test of this 6-low-pan evaluation kit and found the range to be very poor. Other road testers seemed to fare better, but my thought was that the antenna on the hub might be to blame. Seeing as Tariq was so nice as to send me this antenna sample kit, I thought it would be wrong of me not to at least try using one of them. I've chosen the Molex 105.262.868/915 MHz ISM band standalone flexible antenna for the purposes of this project, as it matches the bands that the 6-low-pan module operates on. The antenna itself is constructed as printed traces on a flexible PCB substrate, which can be seen when held at a specific angle to the light. The traces are connected to a coaxial cable by solder joints. The rear of the antenna features 3M double-sided adhesive to adhere the antenna to a case, providing a degree of separation from objects that could interfere with optimum signal radiation. The end of the coax comes pre-terminated in a connector for connection to modules which are designed for external antennas. The IDT kit consists of two components, the first being the battery-powered sensor cube. The 6-low-pan module and surface mount antenna can be seen on the bottom, with a provision to connect an external antenna. While I could attach the antenna here, I don't think this part of the kit is the main problem. The other part of the kit is the hat that attaches to a Raspberry Pi, which forms the hub. The hub PCB has no provision for an external antenna and uses a printed trace pattern to approximate a helical antenna. The wires are poorly machined with an offset, and the solder mask isn't well aligned either. This type of antenna is likely to compromise performance. In order to fit an external antenna, I propose cutting the trace to the existing antenna, scraping away some solder resist, and soldering the coax directly to the board on the assumption that the circuit is matched for a 50 ohm antenna. I start by snipping off the connector and attempting to strip the coax. Being so fine in terms of the outer braid, this proved to be a bit of a finicky challenge. I found that my cut went too deep, breaking off too many of the strands of the shielding, so instead I stripped back the outer shielding entirely and aimed to strip the center conductor instead. This is a success, and so I twist the center conductor strands together, ready for tinning. To strip the outer insulation, I decide to get my knife and instead make a shallow cut into the insulation. This gives me just enough traction so that I can pull off just a little amount of insulation so that I can have a small amount of braid twisted together for tinning. The wires are now tinned, and the attention can be shifted over to the PCB. As I don't have a fiberglass pen, I'm resorting to using my knife to both carve away traces and scratch away the solder resists. This must be done for the antenna conductor to isolate the existing antenna from the module. The exposed copper is tinned, and the connection is made by reflowing the solder while precariously holding everything in alignment. The ground connection is made to the ground plane beside the antenna connection in much the same fashion. So there we have it, modification complete. Now we can piece it back together with the Raspberry Pi Zero W it came with. Luckily, as the case has some clearance near the top, the antenna wire can be routed around to let the antenna sit outside the enclosure, potentially in a better location that interferes less with the radiation pattern. So how does it perform? Well, in a word, better. There's about a 6 to 10 dB gain in reported RSSI from the cube and a doubling of the achieved range. There also seems to be some non-linearity in the reported RSSI values, perhaps due to the module's design, radiation pattern issues on the sensor cube's antenna, combined with a new hub antenna, or signal multipath influences from the test environment. Unfortunately, the range is still not as good as I would have expected, which is around 30 meters based on back-of-the-envelope calculations. The fact that the hub being next to the cube reports a signal strength of minus 41 dBm suggests there's about a 51 dB system loss already at zero distance, implying that there is some, perhaps bigger improvement to be made by also improving the cube's antenna. The other possibility is that the unit may be defective from the outset, for example, damage to the RF stages via ESD, causing the transmission power to be much less than expected. So there we have it, a project using one of the provided sample antennas. While it didn't restore the system to performance levels which I would have expected, it did double the range and provide about a 9 dB advantage, which is quite sizable even though my soldering is perhaps subpar, and the assumptions of a 50 ohm match may not be correct. But it does illustrate the point that having a better antenna and providing some space from the items which may affect the antenna's performance can give much better results. The result does point to the sensor cube antenna perhaps being part of the issue as well. Remember, a system always has multiple parts, and the antenna there may have an odd radiation pattern and polarization mismatch, causing further signal loss. Finally, the RSSI indication could be at fault as well. It may not be entirely linear, as it's not a calibrated value. This has been Goff Louis for the RF Project 14 at Element 14 in November 2019. Thank you for watching.